We've now almost completed our journey. This will be it for talking about several kinds of learning. The venerable kind, that's the nearest neighbors and decision tree or identification tree types of learning. Still useful, still the right thing to do if there's no reason not to do the simple thing. Then we have the biologically inspired approaches, neural nets, all kinds of problems with local maxima and overfitting and oscillation if you get the rate constant too big. I don't know. Genetic algorithms, like neural nets, both are very naive in their attempt to mimic nature. So maybe they work on a class of problems. They surely do. Each have a class of problems for which they're good, but as a general purpose, first resort, don't recommend it. But now the theorists have come out and done some things that are very remarkable. And in the end, you have to say, wow, these are such powerful ideas. I wonder if nature has discovered them too. Is there good engineering in the brain based on good science? Or given the nature of evolution, is it just random junk that isn't the best way for doing anything? Who knows? But today we're going to talk about an idea I'll bet is in there somewhere because it's easy to implement. It's extremely powerful in what it does. And it's the essential item in anybody's repertoire of learning mechanisms. It's also a mechanism which, if you understand only by formula, you will never be able to work the problems on the quiz, that's for sure. Because on the surface, it looks like it'd be very complicated to simulate this approach. But once you understand how it works and look at a little bit of the math and let it sing songs to you, it turns out to be extremely easy. So it's about letting multiple methods work in your behalf. So far, we've been talking about using just one method to do something. And what we're going to do now is we're going to look to see if a crowd can be smarter than the participants, than the individuals in the crowd. But before we get too far down that abstract path, let me just say that the whole works has to do with classification and binary classification. You know, am I holding a piece of chalk in my hand or a hand grenade? Is that a cup of coffee or tea? Those are binary classification problems. And so we're going to be talking today strictly about binary classification. We're not going to be talking about finding the right letter in the alphabet that's written on the page. That's a 26-way choice. We're talking about binary choices. So we assume that there's a set of classifiers that we can draw on. Here's one, H. And it produces either a -1 or a +1. So that's how the classification is done. If it's coffee, +1. If it's tea, -1. If it's chalk, +1. If it's a hand grenade, -1. So that's how the classification works. Now, too bad for us, normally the world doesn't give us very good classifiers. So if we look at the error rate of this classifier or any other classifier, that error rate will range from 0 to 1 in terms of the fraction of the cases got wrong on a sample set. So you'd like your error rate to be way down here. You're dead if it's over there. But what about in the middle? What if it's, say, right there, just a little bit better than flipping a coin? If it's just a little bit better than flipping a coin, that's a weak classifier. And the question is, can you make a classifier that's way over here, like there, a strong classifier by combining several of these weak classifiers and letting them vote? So how would you do that? You might say, well, let us make a big classifier, capital H, that works on some sample X. And as its output, produces something that depends on the sum of the outputs of the individual classifiers. So we have H1 working on X. We have H2 working on X. And we have H3 also working on X. Say 3 of them just to start us off. And now let's add those guys up and take the sign of the output. So if 2 out of the 3 of those guys agree, then we'll get an either +1 or -1. If all 3 agree, we'll get +1 or -1, because we're just taking the sign. We're just taking the sign of the sum of these guys. So this means that one guy can be wrong as long as the other 2 guys are right. But I think it's easier to see how this all works if you think of some space of samples. And you say, well, let's let that area here be where H1 wrong. And this area over here is where H2 is wrong. And then this area over here is where H3 is wrong. So if the situation is like that, then this formula always gives you the right answers on the samples. I'm going to stop saying that right now because I want it to be kind of a background thing on the sample set. We're talking about wrapping this stuff over the sample set. Later on, we'll ask, okay, given that you trained this thing on a sample set, how well does it do on some new examples? Because we want to ask ourselves about overfitting questions. But for now, we just want to look and see if we believe that this arrangement, where each of these guys, each of these H's is producing +1 or -1, we're adding them up and taking the sign, is that going to give us a better result than the tests individually? And if they look like this when draped over a sample set, then it's clear that we're going to get the right answer every time, because there's no area here where any 2 of those tests are giving us the wrong answer. So the 2 that are getting the right answer in this little circle here for H1, these other 2 are getting the right answer, so they'll vote it, and you'll get the right answer every time. But I don't know, it doesn't have to be that simple. It could look like this. There could be a situation where this is H1, wrong answer. This is H2, wrong answer. And this is H3, wrong answer. And now the situation gets a little bit more murky because we have to ask ourselves whether that area where 2 out of the 3 or 3 out of the 3 get it wrong is sufficiently big so as to be worse than one of the individual tests. So if you look at that Venn diagram and stare at it long enough and try some things, you can say, well, there is no case where this will give a worse answer. Or you might end up with the conclusion that there are cases where we can arrange those circles such that the voting scheme will give an answer that's worse than an individual test. But I'm not going to tell you the answer because I think we'll make that a quiz question. So, good idea? Okay. So we'll make that a quiz question. So that looks like a good idea, and we can sort of construct a little algorithm that will help us pick the particular weak classifiers to plug in here. We got a whole bag of classifiers. We got H1, we got H2, we got H55. We got a lot of them we can choose from. So what we're going to do is we're going to use the data undisturbed to produce H1. We're just going to try all the tests on the data and see which one gives us the smallest error rate. And that's a good guy, so we're going to use that. Then we're going to use the data with an exaggeration. Of H1 errors. In other words, this is a critical idea. What we're going to do is we're going we're going to run this algorithm again, but instead of just looking at the number of samples that are got wrong, what we're going to do is we're going to look at a distorted set of samples where the ones we're not doing well on has an exaggerated effect on the result. So we're going to weight them or multiply them or do something so that we're going to pay more attention to the samples on which H1 produces an error, and that's going to give us H2. And then we're going to do it one more time because we've got 3 things to go with here in this particular little exploratory scheme. And this time we're going to have an exaggeration of those samples. Which samples are we going to exaggerate now? We're going to exaggerate, we're going to look for the ones where, we might as well look for the ones where H1 gives us a different answer from H2, because we want to be on the good guy's side. So we can say, we're going to exaggerate those samples for which H1 gives us a different result from H2. And that's going to give us H3. All right, so we can think of this whole works here as part 1 of a multi-part idea. So let's see, I don't know, what might be step 2? Well, if this is a good idea, then what we've got, we can easily derive from that is a little tree to look like this, and we can say that H of X depends on H1, H2, and H3. But now, if that's a good idea, and that gives us a better answer than any of the individual tests, maybe we can make this idea a little bit recursive and say, well, maybe H1 is actually not an atomic test, but maybe it's the vote of 3 other tests. So we can make a little tree structure that looks like this. So this is H11, H12, H13, and then 3 here, and then this will be H31, H32, H33. And so that's a sort of get out the vote idea. Where we're trying to get a whole bunch of individual tests into the act. So the reason this, I guess the reason this wasn't discovered until about 10 years ago was because you got to get so many of these ducks all lined up before the idea gets through that long filter of ideas. So that's only idea number 2 of quite a few. Well, the next thing we might think is, well, we keep talking about these classifiers. What kind of classifiers are we talking about? I've got, oh, shoot, I've spent my last nickel. I don't have a coin to flip, but that's one classifier, right? The trouble with that classifier is it's not a weak classifier because it gives me a 50-50 chance of being right. Well, I guess there are conditions in which a coin flip is better than is a weak classifier. If the 2 outcomes are not equally probable, then a coin flip is a perfectly good weak classifier. But I don't know. What we're going to do is we're going to think in terms of a different set of classifiers, and we're going to call them decision tree. Well, you remember decision trees, right? But we're not going to build decision trees. We're going to use decision tree stumps. So if we have a 2-dimensional space that looks like this, then a decision tree stump is a single test. It's not a complete tree that will divide up the samples into homogeneous groups. It's just what you can do with one test. So each possible test is a classifier. How many tests do we get out of that? 12, right? Yeah, it doesn't look like 12 to me either, but here's how you get to 12. One decision tree test you can stick in there would be that test right there. And that would be a complete decision tree stump. But, of course, you could also put in this one. That would be another decision tree stump. Now, for this one on the right, I could say everything on the right is a minus. Or I could say everything on the right is a plus. It happened to be wrong, but it's a valid test with a valid outcome. So that's how we double the number of tests that we have lines for. And you know what? We can even have a kind of test out here that says that everything is plus, or everything is wrong. So for each dimension, the number of decision tree stumps is the number of lines I can put in times 2. And then I got 2 dimensions here. That's how I got the 12. So there are 3 lines. I can have the pluses on either the left or the right side, so that's 6. And then I got 2 dimensions, so that gives me 12. So that's the decision tree stump idea. And here are the other decision tree boundaries. We obviously just like that. All right, so that's one way you can generate tests, a batch of tests to try out with this idea of using a lot of tests to help you get the job done.
Can you also have a decision tree on the right side? Or is that...
Well, you don't need, the question is, can you also have a test on the right side? See, this is just a stand-in for saying everything's plus or everything's minus. So it doesn't matter where you put the line. It can be on the right side or the left side, the bottom or the top. Or you don't have to put the line anywhere. It's just an extra test in addition to the ones you put between the samples. So does this whole idea of boosting, the main idea of the day, does it depend on using decision tree stumps? The answer is no. Do not be confused. You can use boosting with any kind of classifier. So why do I use decision tree stumps today? Because it makes my life easy. We can look at it, we can see what it's doing. But we could put a bunch of neural nets in there. We could put a bunch of real decision trees in there. We could put a bunch of nearest neighbor things in there. The boosting idea doesn't care. I just use these decision tree stumps because I and everybody else use them for illustration. All right, so we're making progress. Now, what's the error rate for any of these tests and lines we drew? Well, I guess it will be the sum. The error rate is equal to the sum of 1 over n. That's the total number of points, number of samples, summed over the cases where we are wrong. All right? So, gee, you know, we're going to kind of work on combining some of these ideas, and we get this notion of exaggeration. At some stage in what we're doing here, we're going to want to be able to exaggerate the effect of some errors relative to other errors. So one thing we can do is we can assume, or we can stipulate, or we can assert that each of these samples has a weight associated with it. That's W1, this is W2, and that's W3. And in the beginning, there's no reason to suppose that any one of these is more or less important than any of the other. So in the beginning, W sub I at time step 1 is equal to 1 over n. So the error is just adding up the number of samples that were got wrong. And that will be the fraction of samples that you didn't get right, and that will be the error rate. So what we want to do is we want to say, instead of using this as the error rate for all time, what we want to do is we want to move that over and say that the error rate is equal to the sum over the things you got wrong in the current step times the weights of those that were got wrong. So in step 1, everything's got the same weight, doesn't matter. But if we find a way to change the weights going downstream so as to, for example, highly exaggerate that third sample, then W3 will go up relative to W1 and W2. But one thing we want to be sure of is no matter how we adjust the weights, that the sum of the weights over the whole space is equal to 1. So in other words, we want to choose the weights so that they emphasize some of the samples, but we also want to put a constraint on the weights such that all of them added together is summing to 1, and we'll say that that enforces a distribution. A distribution is a set of weights that sum to 1. Well, that's just a nice idea. So we're making a little progress. We've got this idea that we can add some plus minus 1 classifiers together to get a better classifier. We got some idea about how to do that. It occurs to us that maybe we want to get a lot of classifiers into the act somehow or another. And maybe we want to just think about using decision tree stumps so as to kind of ground our thinking about all this stuff. So next step is to say, well, how actually should we combine this stuff? And you will find in the literature libraries full of papers that do stuff like that. And that was state of the art for quite a few years. But then people began to say, well, maybe we can build up this classifier h of x in multiple steps and get a lot of classifiers into the act. So maybe we can say that the classifier is the sign of h, that's the one we pick first. That's the classifier we pick first. That's looking at samples. And then we got h2, and then we got h3, and then we got how many other classifiers we might want, or how many classifiers we might need in order to correctly classify everything in our sample set. So people began to think about whether there might be a way, an algorithm that would develop a classifier that way, one step at a time. That's why I put that step number in the exponent, because we're picking this one at first, then we're expanding it to have 2, and then we're expanding it to have 3, and so on. And each of those individual classifiers are separately looking at the sample. But of course, it would be natural to suppose that just adding things up wouldn't be enough, and it's not. So it isn't too hard to invent the next idea, which is to modify this thing just a little bit by doing what? It looks almost like a scoring polynomial, doesn't it? So what would we do to tart this up a little bit? Come again? Do what? Somewhere out there, someone's murmuring, add weights. Excellent, good idea. So what we're going to do is we're going to have alphas associated with each of these classifiers. And we're going to determine if somebody can build that kind of formula to do the job. So maybe I ought to modify this gold star idea before I get too far downstream. And we're going to say, we're not going to treat everybody in a crowd equally. We're going to weight some of the opinions more than others. And by the way, they're all going to make errors in different parts of the space. So maybe it's not the wisdom of even a weighted crowd, but a crowd of experts, each of which is good at different parts of the space. So anyhow, we got this formula, and there are a few things that one can say sort of turn out. But first, let's write down a sort of algorithm for what this ought to look like. Before I run out of space, I think I'll exploit the right-hand board here and put the overall algorithm right here. So we're going to start out by letting the weights, all of the weights at time 1 be equal to 1 over n. That's just saying that they're all equal in the beginning, and they're equal to 1 over n, and n is the number of samples. And then when I got that, I want to compute alpha somehow. Let's see. No, I don't want to do that. I want to pick a test. I want to pick a classifier that minimizes the error rate. Minimizes error at time t, and that's going to be at time t. And we're going to come back in here. That's why we put a time or step index in there. So once we've picked a classifier that produces an error rate, then we can use the error rate to determine the alpha. So I want the alpha over here. That'll be sort of a byproduct of picking that test. And then with all that stuff in hand, maybe that will be enough to calculate WT plus 1. So we're going to use that classifier that we just picked to get some revised weights, and then we're going to go around that loop until this classifier produces a perfect set of conclusions on all the sample data. So that's going to be our overall strategy. So maybe we've got, if we're going to number these things, that's the fourth big idea, and this arrangement here is the fifth big idea. But then we got the sixth big idea, and the sixth big idea says this. Suppose that the weight on the ith sample at time t plus 1 is equal to the weight at time t of that same, on that same sample divided by some normalizing factor times e to the minus alpha at time t times h at time t times some function y, which is a function of x, but not a function of time. And you say, where did this come from? And the answer is, it did not spring from the heart of a mathematician in the first 10 minutes that they looked at this problem. In fact, when I asked Shapiri how this worked, he said, well, he was thinking about this on the couch every Saturday for about a year, and his wife was getting pretty sore, but he finally found it and saved their marriage. So where does stuff like this come from? Really, it comes from knowing a lot of mathematics and seeing a lot of situations and knowing that something like this might be mathematically convenient. Something like this might be mathematically convenient. But we got to let it see. We got to back up and let it sing to us. What's y? Oh, we saw y last time in support vector machines. That's just a function that's plus 1 or minus 1, depending on whether the output ought to be plus 1 or minus 1. So if this guy is giving the correct answer, and the correct answer is plus, then this guy will be plus 1 too, because it always gives you the correct answer. So in that case where this guy is giving you the right answer, these will have the same sign, so that will be a plus 1 combination. On the other hand, if that guy's giving the wrong answer, you're going to get a minus 1 out of that combination. So it's true even if the right answer should be minus, right? So if the right answer should be minus and this is plus, then this will be minus 1, and the whole combination will give you minus 1 again. In other words, the y just flips the sign if you got the wrong answer, no matter whether the wrong answer is plus 1 or minus 1. These alphas, shoot, those are the same alphas that are in this formula up here somehow. And then that z, what's that for? Well, if you just look at the previous weights and this exponential function to produce these w's for the next generation, that's not going to be a distribution because they won't sum up to 1. So what this thing here, this z is, That's a sort of normalizer. And that makes that whole combination of new weights add up to 1. So it's whatever you got by adding up all of those guys and then dividing by that number. Well, whew. I don't know. Now there's some, it turns out that's. We're going to do, or rather we're going to imagine that somebody's done the same sort of thing we did to support vector machines. We're going to find a way to minimize the error. And the error we're going to minimize is the error produced by that whole thing up there in 4. We're going to minimize the error of that entire expression as we go along. And what we discover when we do the appropriate differentiations and stuff, you know, that's what we do in calculus. What we discover is that we get minimum error for whole thing if alpha is equal to 1 minus the error rate at time t divided by the error rate at time t. But let's take the logarithm of that and multiply by 1/2. And that's what Shapiro was struggling to find. But I haven't quite got it right. And so let me add this in separate chalk so we don't get confused about this. It's a bound on that expression up there. It's a bound on the error rate produced by that expression. So interestingly enough, this means that the error rate can actually go up as you add terms to this formula. All you know is that the error rate is going to be bounded by an exponentially decaying function. So it's eventually guaranteed to converge on 0. So it's a minimal error bound that turns out to be exponential. Well, there it is. We're done. Would you like to see a demonstration? Yeah, okay. Because, you know, you look at that and you say, well, how can anything like that possibly work? And the answer is, surprisingly enough, here's what happens. There's a simple little example. So that's the first test chosen. The greens are pluses and the reds are minuses, so it's still got an error. Still got an error, boom, there in 2 steps. It now has, we can look in the upper right-hand corner. We see it's used 3 classifiers. And we see that one of those classifiers says that everybody belongs to a particular class, 3 different weights. And the error rate has converged to 0. So let's look at a couple of other ones. Here's the one I use for debugging this thing. We'll let that run. See how fast it is? Boom. It converges to getting all the samples right very fast. Here's another one. Oh, this is one we gave under the exam a few years back. First test. Oh, I let it run, so it got everything instantaneously right. Let's take that through step at a time. There's the first one. Second one. Still got a lot of errors. The error rate's dropping. And then it flattened, then it goes to 0. Cool, don't you think? But you say to me, well, who cares about that stuff? Let's try something more interesting. There's one. Oh, that was pretty fast, too. Well, there are not too many samples here, so I don't know. We can try this. So there's an array of pluses and minuses. Boom. You can see how that error rate is kind of bounded by an exponential. So in a bottom graph, you've got the number of classifiers involved, and that goes up to a total eventually of 10. You can sort of see how positive or negative each of the classifiers is by looking at this particular tab. And this just shows how they evolve over time. But the progress thing here is the most interesting. And now you say to me, well, how did the machine do that? And it's all right here. We use an alpha that looks like this. And that allows us to compute the new weights. As soon as we got a preliminary calculation, we got to find a z that does the normalization. And we sure better bring our calculator because we've got, first of all, to calculate the error rate. Then we got to take its logarithm, divide by 2, plug it into that formula, take the exponent, and then that gives us the new weight. And that's how the program works. And if you try that, I guarantee you will flunk the exam. Now, I don't care about my computer. I really don't. It's a slave, and it can calculate these logarithms and exponentials till it turns blue, and I don't care, because I've got 4 cores or something, and who cares? Might as well do this and sit around just burning up heat. But you don't want to do that. So what you want to do is you want to know how to do this sort of thing more expeditiously. So we're going to have to let the math kind of sing to us a little bit with a view toward finding better ways of doing this sort of thing. So let's do that. And we're going to run out of space here before long, so let me reclaim as much of this board as I can. So what I'm going to do is I'm going to say, well, now that we've got this formula for alpha that relates alpha t to the error, then I can plug that into this formula up here, number 6, and what I'll get is that the weight at t plus 1 is equal to the weight at t divided by that normalizing factor multiplied times something that depends on whether it's categorized correctly or not. That's what that y is in there for, right? So we got a logarithm here, and we got a sign flipper up there in terms of that h of x and y combination. So if the sign of that whole thing, that minus alpha, and that y, h combination, turns out to be negative, then we're going to have to flip the numerator and denominator here in this logarithm, right? And oh, by the way, since we got a half out here, that turns out to be the square root of that term inside the logarithm, right? So when we carefully do that, what we discover is that it depends on whether it's the right thing or not. But what it turns out to be is something like a multiplier of the square root. Better be careful here. Square root of what? Well, let's see, but we have to be careful. So let's suppose that this is for things that we get correct. So if we get it correct, then we're going to get the same sign out of h of x and y. We've got a minus sign out there, so we're going to flip the numerator and denominator. So we're going to get the square root of e of t over 1 minus epsilon of t if it's correct. If it's wrong, it'll just be the flip of that. So it'll be the square root of 1 minus the error rate over the error rate. Everybody with me on that? I think that's right. If it's wrong, I'll have to hang myself and wear a paper bag over my head like I did last year, but let's see if we can make this go right correctly this time. So now we've got this guy here. We've got everything plugged in all right. And we know that now this z ought to be selected so that it's equal to the sum of this guy multiplied by these things as appropriate for whether it's correct or not. Because we want, in the end, for all of these w's to add up to 1. So let's see what they add up to without the z there. So what we know is that it must be the case that if we add over the correct ones, we get the square root of the error rate over 1 minus the error rate of the wt plus 1, wt, sorry, plus, now we got the sum of 1 minus the error rate over the error rate times the sum of the wi at time t for wrong. So that's what we get if we added all these up without the z. So since everything has to add up to 1, then z ought to be equal to this sum. Right? And that looks pretty horrible until we realize that if we add these guys up over the weights that are wrong, that is the error rate. This is E. So therefore, z is equal to the square root of the error rate times 1 minus the error rate. That's the contribution of this term. And now let's see, what is the sum of the weights over the ones that are correct? Well, that must be 1 minus the error rate. So this thing gives you the same term, the same result as this one. So z is equal to 2 times that. And that's a good thing. Now we are getting somewhere, because now it becomes a little bit easier to write some things down. Oh, we're way past this, so let's get rid of this. And now we can put some things together. Let me point out what I'm putting together. I've got an expression for z right here. And I got an expression for the new w's here. So let's put those together and say that w of t plus 1 is equal to w of t. I guess we're going to divide that by 2. And then we got this square root times that expression. So if we take that correct one and divide by that one, then the e sub t cancel out, and I get 1 over 1 minus the error rate. That's if it's correct. And if it's not correct, then it's Wt over 2, working through the math, 1 over epsilon, if wrong. Do we feel like we're making any progress? No, we don't, because we haven't let it sing to us enough yet. So I want to draw your attention to what happens to amateur rock climbers when they're sort of halfway up a difficult cliff. They're usually belayed, sometimes they're not. If they're not, they're scared to death. And every once in a while, as they're just about to fall, they find some little tiny hole to stick a fingernail in, and that keeps them from falling. That's called a thank God hole. So what I'm about to introduce is the analog of those little places where you can stick your fingernail in. It's the thank God hole for dealing with boosting problems. All right? So what happens if I add all these wi up for the ones that the classifier produces a correct answer on? Well, it'll be 1 over 2 and 1 over 1 minus epsilon times the sum of the w sub t for which the answer was correct. What's this sum? Oh, my God, it's 1 minus epsilon. So what I've just discovered is that if I sum the new w's over the correct, those samples for which I got a correct answer, it's equal to 1/2. And guess what? That means that if I sum them over wrong, it's equal to 1/2 as well. So that means that I take all of the weights for which I got the right answer with the previous test, and those weights will add up to something. And to get the weights for the next generation, all I have to do is scale them so that they equal half. This was not noticed by the people who developed this stuff. This was noticed by Luis Ortiz, who was a 6034 instructor a few years ago. The sum of those weights is going to be a scaled version of what they were before. So you take all the weights for which this new classifier, this one you selected to give you the minimum weight on the reweighted stuff, you take the ones that it gives a correct answer for, and you take all those weights and you just scale them so that they add up to a half. So do you have to compute any logarithms? No. Do you have to compute any exponentials? No. Do you have to calculate z? No. Do you have to calculate alpha to get the new weights? No. All you have to do is scale them. And that's a pretty good thank God hole. So that's thank God hole number one. Now, for thank God hole number two, we need to go back and think about the fact that we're going to give you problems in all probability that involve decision tree stumps. And there are a lot of decision tree stumps that you might have to pick from. So we need a thank God hole for deciding how to deal with that. Oh, where can I find some room? How about right here? Suppose you've got a space that looks like this. I'm just making this up at random. So how many, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many tests do I have to consider in that dimension? 11. It's 1 plus the number of samples. That would be horrible. I don't know. Do I have to actually calculate this one? How could that possibly be better than that one? It's got one more thing wrong. So this one, that one makes sense. The other one doesn't make sense. So in the end, no test that lies between two correctly classified samples will ever be any good. So that one's a good guy, and that one's a good guy, and this one's a bad guy, a bad guy, bad guy, bad guy, bad guy, bad guy, bad guy, bad guy. So the actual number of tests you've got is 3. And likewise, in the other dimension, well, I haven't drawn it so well here, but can this test be a good one? No. That one, no, because actually, I better look over here on the right and see what I've got before I draw too many conclusions. Let's leave it with this, since I don't want to think too hard about what's going on in the other dimension. But the idea is that very few of those tests actually matter. Now you say to me, there's one last thing. What about overfitting? Because all this does is drape a solution over the samples. And like, support vector machines overfit, neural nets overfit, decision identification trees overfit. Guess what? This doesn't seem to overfit. That's an experimental result for which the literature is confused with respect to providing an explanation. So this stuff is tried on all sorts of problems like handwriting recognition, understanding speech, all sorts of stuff uses boosting. And unlike other methods, for some reason, as yet imperfectly understood, it doesn't seem to overfit. But in the end, leaving no stone unturned at 6034, every time we do this, we do some additional experiments. So here's a sample that I'll leave you with. Here's a situation in which we have a 10-dimensional space. We've made a fake distribution, and then we put in that boxed outlier. That was just put into the space at random, so it can be viewed as an error point. So now what we're going to do is we're going to see what happens when we run that guy. And sure enough, in 17 steps, it finds a solution. But maybe it's overfit that little guy who's an error. Well, one thing you can do is you can say, well, all of these classifiers are dividing the space up into chunks and we can compute the size of the space occupied by any sample. So one thing we can do, alas, I'll have to get up a new demonstration. One thing we can do, now that this guy's over here, we can switch to the volume tab and watch how the volume occupied by that error point evolves as we solve the problem. So look what happens. This is, of course, randomly generated. I'm counting on this working. Never failed before. So it originally starts out as occupying 26% of the total volume and ends up occupying 1.4 times 10 to the minus third percent of the volume. So what tends to happen is that these decision tree stumps tend to wrap themselves so tightly around the error points, there's no room for overfitting because nothing else will fit in that same volume. So that's why I think that this thing tends to produce solutions which don't overfit. So, in conclusion, this is magic. You always want to use it. It will work with any kind of suite of classifiers you want, and you should understand it very thoroughly because this, if anything, is useful in the subject in the dimension of learning. This is it.